Hello again. This is Math 2, 115 coming to you from the College of DuPage, and the title of this lecture is The Pigeonhole Principle. Make sure you're an active learner as you watch this video. The Pigeonhole Principle states that if n pigeons fly into m pigeonholes, and n, the number of pigeons, is greater than the number of pigeonholes, then at least one hole must contain 2 or more pigeons. And we can look down here. We have an example of 5 pigeons, and we have 4 pigeonholes, and you see that 2 of them have to land in the same hole. And you can look at this over here also just with a mapping, and you can see that pigeon 1 and pigeon 4, both in this case, go to 3. Okay, the pigeonhole principle is sometimes called the Dirichlet box principle because it was first stated by this great mathematician long ago. Now, that was not really in math speak, so here's what we will say in math speak for the pigeonhole principle. A function from one finite set to a smaller finite set cannot be one-to-one. There must be at least 2 elements in the domain that have the same image under that mapping in the codomain. Now, this is a very simple idea, but the applications range from very simple to extremely subtle and complex. Let's look at a few of them. In a group of 6 people, must there be at least 2 who were born in the same month? And the answer to that is no, because it could be born in January, February, all the way through June. So, in a group of 13 people, must there be at least 2 who are born in the same month? And the answer to that is yes, because the 13 people are pigeons, and the 12 months are pigeonholes. A more complicated example. Among the residents of New York City, why must there be at least 2 people with the same number of hairs on their head, and why? Let's talk a little bit more about this. The answer is yes. Okay, so the pigeons are the people of New York City, and the pigeonholes are all possible numbers of hair on any individual's head. Now, so what we have is the people in New York City, a whole bunch of them, and we know that that number is about 8 million. And the number of hairs on a person's head, a person could be totally bald, or the maximum number of hair ends up being 300,000. And that's actually an interesting number to calculate, and you'd have to think about things we know from anatomy about that. It actually depends on hair color and things like that. But it can be shown that the maximum number of hairs on any person's head is less than 300,000. So we can define a function from the set of people in New York to the numbers 0 through 300,000, and that's what we have here. So you see, since the number of people in New York is larger than the number of possible heads on their hair, this is not one-to-one, and that means at least 2 arrows point to the same number. This means that at least 2 people have the same number of hairs on their head. This is another kind of problem that you can run across, and this is a nice one that I often ask on exams. Perhaps not as simple as this, but using this concept. Finding the number to pick to ensure a result. So suppose you have a drawer containing 10 black and 10 white socks. You reach in and pull out without looking at them. What's the least number of socks you must pull out to be sure you get a matched pair? And explain your answer using the pigeonhole principle. Well, you see, in this case, the pigeonholes are the colors of the socks, and the socks are numbered 1 through, I guess this is 20. In this case, there were 20. And so what you're really doing is you're saying, to get a matching color, if I just pick 1 sock, I certainly wouldn't have a matching pair. If I pick 2, they might be white and black. But if I pick 3, I have to have a matching pair. That means you have to pick at least 3 socks before two of them have the same color. Problems continue. Select a pair of integers with a certain sum. Suppose that A is a set 1, 2, 3, 4, 5, 6, 7, and 8. If 5 integers are selected from A, must at least one pair of the integers have a sum of 9. Let's talk about this problem. And the answer is yes. Because we can partition, see how we're using all the words we've talked about before, the set A into the following 4 disjoint subsets. And notice that these are the subsets that add to be 9. Observe that each of the integers in A occurs in exactly one of these. That's what it means to be a partition. And that the sum of all of them is 9. Thus, if the 5 integers from A are chosen, so we're picking 5 here, but there are 4 pigeonholes. So, 2 must be from the same subset, and it follows that the sum of them is 9. And here's the 5 numbers that we're picking, and we map them into there, and you can see that there's 5 of these and 4 of those, so that makes sense. And let's look at another problem, B. If 4 integers selected from A, must at least one pair have a sum of 9? Well, the answer to this one is no. This is a case where the pigeonhole principle does not apply because the number of pigeons is not larger than the number of pigeonholes. So, for instance, if you select 1, 2, 3, and 4, then the largest sum that would be possible would be 7, and no 2 add up to 9. There are math majors in this class, and this is a good example. I know you know this fact, but I don't know if you know how to prove it. We'll prove it now using the Pigeonhole Principle. So the decimal expansion of any rational number either terminates or repeats. So a terminating decimal is one that ends, and a repeating decimal is one that you have some digits that are repeating over and over and over again. Okay, so let's think about that then. See, a rational number is going to be the ratio of integers. And so here we have 4 over 33. And so if we wanted to figure out what 4 over 33 is, we would start dividing. And eventually you would see the 2 1 starts repeating. So that's an example of this because whenever you get 4 and 4 down here, you're going to get the same thing if you keep going. And so that's the idea behind the proof. And in fact, here is more of a proof. And here we're doing even another example. We have 3 over 14. We do it, and you see we go for a long way. But what happens is we get a 4 here, and we get another 4 down here. And so you see that this is going to repeat. So what we're doing is we're showing that that is repeating. Okay, so we let R0 equal A, and the rest of these be the remainders that are possible when we divide by this. So in this case, we would get remainders that would be 0 through 13. But this is a sequence of remainders that go along. But when we're dividing by this, we're talking about the sequence of remainders. And so you see what happens is, and we're taking each. These are the remainders that we get when we're dividing in general. So we know that each remainder must be between 0 and b minus 1, and we're talking about a over b. And so what happens is that there's only a finite number of these, and this is the sequence, and so 2 of these have to be mapped to the same thing. Now note that since the decimal expansion of any rational number either terminates or repeats, if a number has a decimal expansion that neither terminates nor repeats, this is using, like a De Morgan's law or a law of contraposition, then it cannot be rational. Thus, for example, this number, where each string of ones is one longer than the previous string, has to be irrational. This is a proof that there are irrational numbers without using the square root of 2 as the example. We come now to the generalized pigeonhole principle. And this is the generalization. And here you see that we have, let's see, must be one, yeah, it looks like we have 9 pigeons, okay, and we have 4 pigeonholes. So this is the generalization. If n pigeons fly into m pigeonholes, and for some positive integer k, where k times m is less than n, then at least one pigeonhole must contain k plus 1 or more pigeons. And that's kind of complicated to think about, but let's look down here. We have 9 pigeons, and we have 4 pigeonholes. So when we start mapping the pigeons to the pigeonholes, we have to have at least one pigeonhole where there are 3. And so you see, m in our case was 4, n was 9, and k was 2. So since 2 times 4 is 8, less than 9, then at least one pigeonhole must contain 2 plus 1 or more pigeons. And certainly all the pigeons could go into one hole, but we're talking about at least. So if we state this in math speak, here's how we would state the generalized pigeonhole principle. For any function f from a finite set x with n elements to a finite set y with m elements, and for any positive integer k, if k times m is less than n, then there is some y in capital Y, such that y is the image of at least k plus 1 distinct elements of x. So let's apply this to a problem. Show how the generalized pigeonhole principle implies that in a group of 85 people, at least 4 must have the same last initial. Well, there are 85 people, and their last initials can run from A through Z, so there are 26 of these. But since 3 times 26 is 78, and that's less than 85, the generalized pigeonhole principle states that some initial must be the image of at least 4, 3 plus 1 people. Thus, at least 4 people have the same last initial. You really want to think about this a bit. It's not trivial. And also, sometimes the contrapositive form of this is useful. So for any function f from a finite set x with n elements to a finite set y with m elements, and for any positive integer k, if for each y in an element of capital Y set, the inverse function of y has at most k elements, the inverse image of y has at most k elements, then x has at most km elements. In other words, n is less than or equal to k times m. So let's do an example, and this is applying it to the problem we had before. And we're going to do a proof by contradiction. So suppose no 4 people out of the 85 had the same last initial. Then at most 3 would share any particular one. Because you see, if no 4 people, then there's at most 3. And by the generalized principle, then, this would imply that the total number of people is at most 3 times 26, or 78. But that contradicts the fact that there are 85 people in all. Hence, at least 4 people share a last initial. Okay, let's do a little bit more complicated example. There are 42 students who are to share 12 computers. Each student uses exactly 1 computer, and no computer is used by more than 6 students. Show that at least 5 computers are used by 3 or more students. So let's start with an argument by contradiction. Suppose not. Suppose that few or fewer computers are used by 3 or more students. You see, that's the contradiction, because we're assuming, they said at least 5. If it's not at least 5, then it's 4 or fewer. And we'll derive a contradiction. Then 12 minus 4 is 8 or more computers are used by 2 or fewer. Divide the set of computers into 2 subsets, C1 and C2. Into C1, place 8 of the computers used by 2 or fewer students. And into C2, place the computers used by 3 or more students, plus any remaining computers, to make a total of 4 computers in C2. Since at most 6 students, are served by any one computer, by the contrapositive form of the generalized pigeonhole principle, the computers in set C2 serve at most 6 times 4, or 24 students. Since at most 2 students are served by any computer in C1, by the generalized pigeonhole principle, the contrapositive form, the computers here serve at most 2 times 8, or 16 students. Hence, the total number of students served is the sum of the students you have in C1 and C2 is going to be 40. But this contradicts the fact that each of the 42 students is served by a computer. Therefore, the supposition is false. At least 5 computers are used by 3 or more students. Getting more subtle. Yes? Here's a direct argument. And again, it's the same. Well, wait, I think we may, let's see. Yeah, this is the exact same problem, but now we're going to use a direct argument instead of a proof by contradiction. Let K be the number of computers used by 3 or more students. We must show that K is bigger than or equal to 5. Because each computer is used by at most 6 students, these computers are used by at most 6K students. Each of the remaining 12 minus K computers is used by at most 2 students. Hence, taken together, they're used by at most 2 times 12 minus K, or 24 minus 2K. Here we just distributed the 2. Thus, the maximum number of students served by the computers is going to be 6K plus 24 minus 2K, and that is 4K plus 24. Because 42 students are served by the computers, this number must be bigger than or equal to 42. If you solve that inequality for K, you get K is bigger than 4.5. But K is an integer, so if it's bigger than 4.5, it has to be less than or equal to, or excuse me, K has to be greater than or equal to 5. Now we're going to go and talk a little bit about the proof of the pigeonhole principle. Okay? And it depends essentially on the sets involved being finite. And recall that a set is finite if and only if it is either the empty set or there's a one-to-one correspondence from a set that is 1, 2, ... all the way up to n to it, where n is a positive integer. That's really just counting the number of elements there. In the first case, the number of elements is 0, and the second case is said to be n. And a set that is not finite is called infinite. Okay, so thus, any finite set is either empty, or it can be written in the form x sub 1, x sub 2, all the way up to x sub n, where n is a positive integer. Okay, so we're then going to prove this theorem. And again, we're proving the pigeonhole principle. This is the statement we used before. Suppose f is any function from a finite set x with n elements to a finite set y with m elements, and n is greater than m. So denote the elements of y by y1 through y sub m. And for each y sub I in y, the inverse image sets, and that's the inverse image of y sub I is the set of x, an element of x, such that f of x equal y sub I. See, this goes back to our discussions about functions and inverse images. And so we have these inverse image sets, and this is the collection of all those sets. So this is 1, this is the inverse of f for y sub 1, y sub 2, all the way up to y sub n. Now, by the definition of a function, because f was a function, each element of x is sent by f to some element of y. Hence, each element of x is in one of these inverse image sets, one of these. And so the union of all these sets has to equal x. But also, by the definition of function, no element of x is sent by f to more than one element of y. And the reason is it's not sent to more than one by the definition of function, because a function takes things to a unique image. Thus, each element of x is in only one of the inverse image sets. So, the inverse image sets are mutually disjoint. So by the addition rule, the number of things that are in x is going to be the sum of the number that are in these mutually disjoint sets that make up x. Now suppose that f is 1 to 1, and by the way, that is a contradiction now. This is the opposite of what we want to prove. Then each of these has at most one element. If it's 1 to 1, there's only one image there, and so you add them up, and there were m of those, so you get m. Putting the equations together, we say that n is the number of things in x, but that is less than or equal to, you see it was less than or equal to up here, m, which is the number in y. This contradicts the fact that n is bigger than m. Here we're saying n is less or equal to. So the supposition that f is 1 to 1 must be false. Hence, f is not 1 to 1, as was to be shown. Another important theorem that follows from the Pigeonhole Principle states that a function from one finite set to another finite set of the same size is 1 to 1 if and only if it is onto. Now, this is not true for infinite sets. Look at this. This function, y equals f of x equal 2x, is 1 to 1 from the integers, but it's not onto the integers. It's onto a subset of the integers. And so this is an example of a function that is 1 to 1, but not onto. Now, the integers, though, are an infinite set. So you see that's what's going on. Let's look then at the proof of this, and again it hinges on being finite sets. So suppose f is a function from x to y, and x and y are finite sets, and you've got m things here, and you've got m things here as well, each with m things. Okay, now if f is 1 to 1, then it is onto, and this is the proof of that. You see, we have to go both ways. This is if and only if. So if f is 1 to 1, we have to show that it is onto. So we're going to start with the if part. Suppose f is 1 to 1. Then f of x1, f of x2, all the way down to f of xn are all distinct. That's what 1 to 1 means. Consider the set S of all elements of y that are not the image of any element of x. Then the sets, and so here we have the sets of f of x1, f of x2, all the way up to f of xn, and s are mutually disjoint. So by the addition rule, the number in this set is equal to the sum of the number in those sets plus the number in s. So we add those together. We'll get m terms where there are 1s plus n sub s, and this is equal to m plus n sub s. Thus, m is equal to m plus n sub s. And so the number in s, you can solve that equation, has to be 0. Hence, s is an empty set. So there is no element of y that is not the image of some element of x. Consequently, f is onto. So you see we showed if f is 1 to 1, then f is onto. Now we're going to say suppose f is onto, and we have to show that it's 1 to 1. So suppose f is onto. That's our if part. Then for each I, 1 through m, the inverse image of y sub I is not equal to 0. And that's not really 0, that's the null set. And so the number in each of those is bigger than or equal to 1. As in the proof of the Pigeonhole Principle, X is the union of the mutually disjoint sets f of y1, f of y2, all the way through f of ym. So by the addition principle, the number in X is equal to the sum of these, and that's going to be bigger than or equal to m. Now, if any of the sets f inverse y sub I has more than one element, then the sum of the m terms is greater than m. But we know this is not the case because the number in X is equal to m. Hence, each set has exactly one element, and thus f is 1 to 1, as to be shown. Now, we should note that this theorem applies in particular when we got the case x equal y. A 1-to-1 function from a finite set to itself is onto, and an onto function from a finite set to itself is 1-to-1. Such functions are permutations, because it's a rearrangement of the set on which they were defined. For instance, the function defined, and I guess I don't have this diagram, but anyway, it is a permutation. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and each other. God bless you all.